Hey everyone, my name is Joshua Ball, and today I'm presenting my water tower design project for Masabi Primary School in Naguni, Kenya. This project focuses on designing a realistic and structurally safe water storage system that can provide a consistent supply of clean drinking water for the school and surrounding community. I'll start by explaining the problem and why it matters, then walk through the design process, analysis, and how I selected the final design. When we think about engineering problems, a lot of times we think about things like buildings or machines. One of the most important challenges engineers work on is access to basic resources. Clean drinking water is something that directly affects health, education, and overall quality of life. In many rural areas, water systems are not developed, and communities rely on natural sources like rainfall or small storage systems. These systems are often inconsistent and depend heavily on weather conditions. So instead of having a reliable supply, people are constantly dealing with uncertainty, which makes it difficult to plan daily life. This project focuses on using engineering to create a more reliable solution to that problem. The main issue is not just the lack of water, but the lack of reliable and safe access to it. In many rural communities, the only available systems are small rainwater tanks or nearby wells. These sources can easily run out or become contaminated. When that happens, people are forced to travel long distances, sometimes multiple times a day, just to collect water. This creates multiple problems. First, the water quality is often poor, which leads to waterborne diseases. Second, the time spent collecting water takes away from school, work, and other important activities. So the problem is really a combination of availability, safety, and accessibility. At Masabi Primary School, this problem becomes much more clear when you look at the actual situation. The school serves over 600 students and staff, which creates a significant daily demand for water. Even at a minimum estimate of about half a gallon per person per day, that comes out to roughly 300 gallons needed every single day. Right now, the school relies on a small rainwater tank, which isn't able to consistently meet the demand, especially during dry periods when rainfall is limited. So when the tank runs out, students are forced to leave class and walk to distant wells to collect water. And the quality of that water isn't always reliable either. This not only increases the risk of illness, but it also takes time away from learning. Over time, this creates a cycle where both health and education are affected, making it harder for the community to improve their situation. This project also connects to a Christian worldview, specifically the idea of serving others and helping carry their burdens. Galatians 6:2 says, "Carry each other's burdens, and in this way you will fulfill the law of Christ." In this situation, the burden is the daily struggle to access clean water. As engineers, we have the ability to design solutions that directly improve people's lives. This project is an example of using technical knowledge, not just for efficiency or performance, but to meet real human needs. So the design is not just about structure and materials, it's about creating something that has meaningful impact on a community. To begin the design, the first step was identifying key requirements. The structure needed to support the weight of water, resist environmental loads like wind, and remain stable under different conditions. It also needed to be cost effective and use materials that are realistically available. From there, two different design concepts were developed. These designs were intentionally different so that we could compare how size and height affect performance. Once the designs were created, they were modeled in SOLIDWORKS, and both simulation and hand calculations were used to evaluate them. Testing multiple conditions allowed for more complete understanding of how each structure behaves rather than just looking at one scenario. Design A is a compact structure with a 12 by 12 foot base and a height of 4 feet. It supports a cylindrical tank with a capacity of 10 gallons. Because the structure is short, the load is distributed more directly downward, which reduces bending forces. This leads to lower stress and smaller displacement. Design B, on the other hand, is much taller at 60 feet, with a larger 18 by 18 foot base and a 5,000 gallon tank. While it increases storage capacity, the height creates much larger bending moments. The taller the structure, the more leverage wind and loads have to create stress. So design B introduces more complexity and higher internal forces, even though it seems beneficial in terms of capacity. To evaluate the designs, multiple loading conditions were applied. We tested both half-capacity and full-capacity water loads, since the structure needs to perform safely under all possible conditions. We also included wind loading, using both average wind speed and double that value to simulate more extreme conditions. For the hand calculations, free body diagrams were created at key joints. These diagrams allowed us to isolate forces and apply equilibrium equations, like summing forces in the x and y directions. For example, one case we analyzed was design A at half capacity, where the total load was about 7,270 pounds. Since this load is supported by multiple joints, we distributed it across 4 joints, giving about 1,818 pounds per joint. We then created a free body diagram of one joint to isolate the forces, including both vertical and horizontal components. Using equilibrium equations, where the sum of forces in the x and y directions equals 0, we solved for internal forces in members like the diagonal brace and horizontal support. The diagonal member carries more load because it resists both vertical and horizontal forces, while the horizontal member mainly resists lateral forces. In addition to hand calculations, the SOLIDWORKS simulations were used to analyze stress distribution and displacement across the entire structure. Comparing both methods helped validate the results and also showed the limitations of simplified hand analysis compared to full 3D simulations. The results clearly showed a difference between the two designs. For design A, displacement remained very low in all cases, even under full load and increased wind conditions. Stress values also stayed below the material's yield strength, meaning the structure would not fail. For design B, the results were significantly different. Because of the 60-foot height, the top of the structure experienced much larger displacement. This is due to increased bending caused by both vertical loads and lateral wind forces. In several cases, the stress approached or exceeded the yield strength of the material, which indicates that the structure would begin to fail under those conditions. This highlights an important engineering concept. Increasing height increases bending moments, which leads to higher stress and instability. So even though design B had a larger capacity, it was not structurally efficient or safe compared to design A. The conclusion we came to after doing our analysis is that design A would be the much better water tower. The first and most important factor was structural safety. Design A consistently remained below the material's yield strength under all loading conditions, meaning it would not fail. In contrast, Design B exceeded safe stress limits in several cases, especially under full load and higher wind conditions. The next factor was stability and displacement. Design A showed very little movement, which indicates a stable structure. Design B, because of its height, experienced much larger displacement, especially at the top, which is a sign of instability. We also looked at material efficiency. Design A uses less material and has a simpler structure, which makes it more efficient overall. Finally, we considered a real-world feasibility. Design A is easier to build, requires fewer resources, and is more practical for a rural environment where construction capabilities may be limited. Taking all of these factors into account, Design A was selected as the final design which provides the safest, most reliable, and most realistic solution. The final design includes a detailed bill of materials and production drawings. The structure uses steel square tubing for the frame, a steel tank a half-inch thickness, and standard components like bolts and welding materials. The total estimated cost is around $3,655, which makes the design relatively affordable. SOLIDWORKS drawings include all dimensions, member layouts, and connection details. These are essential for guiding construction and ensuring the structure is built correctly. The assembly process was designed to be simple and logical. It starts with constructing the base frame and ensuring it is level. This is important because the entire structure depends on a stable foundation. Next, the vertical members are installed, followed by diagonal bracing, which adds strength and helps resist wind loads. Then, the top platform is assembled and the water tank is installed and secured. Finally, all connections are checked to make sure the structure is aligned and stable. This step-by-step process ensures that the tower can be built efficiently and safely in real-world conditions. To conclude, this project demonstrates how engineering can be used to solve real-world problems. By designing a safe and practical water tower, it can provide a reliable source of clean water which improves health, education, and overall quality of life. It also shows how engineering can go beyond technical performance and be used as a way to serve others and make a meaningful impact. Thank you.